We spent Chapter 2 counting outcomes. Now we build the framework that gives those counts meaning. A probabilistic model has two parts, a sample space and a probability law, and this video builds the first. In this video, we meet the experiment, its outcomes, and the sample space. We define an event. We see why one experiment can have many sample spaces. And we lay down the two rules a sample space must obey. In probability, an experiment is a random occurrence that produces one of several outcomes. Collect every possible outcome into a single set, and you have the sample space, written capital Omega, the same universal set from Chapter 1, now wearing its probability name. Picture it as a box holding one ball for each possible outcome. When you actually run the experiment, exactly one of these balls is realized. That is the outcome. An event is an admissible subset of the sample space, any collection of outcomes we want to ask a question about. Here it is a dashed loop drawn around some of the balls. Make it concrete with the rolling of a die. The sample space is the 6 faces, omega equals 1 through 6. The set of primes less than or equal to 6, 2, 3, and 5 is one event among many, and the number you actually read off the die is the outcome. Sample space, event, outcome, the whole vocabulary on one picture. There is essentially no restriction on what counts as an experiment, and this is the subtle part. The same experiment can have more than one sample space. Take n tosses of a coin. If all you care about is how many heads come up, the natural sample space is just the counts, 0, 1, 2, all the way to n. That is only n plus 1 outcomes. But if you want the complete history, which toss was heads and which was tails in order, then each outcome is a full sequence, and there are 2 to the n of them. Same coins, same tosses, but a far larger sample space. Neither is more correct than the other. The choice of sample space depends on the property you wish to analyze, rich enough to distinguish every outcome you care about, but no more detailed than the question demands. Some freedom then, but not total freedom. A sample space must obey 2 rules. First, its elements must be distinct and mutually exclusive. No 2 outcomes can occur at once, so that the outcome of the experiment is always unique. Second, the sample space must be collectively exhaustive. Every possible outcome has to be accounted for, with nothing left out. Here is a tempting candidate for the die that breaks the first rule: the odd numbers, the even numbers, and the primes. These overlap. 3 and 5 are both odd and prime, and 2 is both prime and even, so a single roll can land in 2 categories at once. The outcome is not unique, so this is not an admissible sample space. Fix it by dropping the primes. The odd numbers and the even numbers are disjoint. No integer is both, and together they cover 1 through 6 completely. Distinct, mutually exclusive, and exhaustive, a partition of the outcomes, and a perfectly valid sample space. So that is half of a probabilistic model, a sample space of all the outcomes with events as its admissible subsets. Next, we give those events numbers, the rules a probability law must obey, the axioms of probability.